Thank you very much. I originally prepared a speech starting ladies and gentlemen, but this is a much more friendly setup. So I would say hello everybody. I'm Shigefumi Moriya, Director of the SGU Mathematics Subunit of Kyoto University. Before starting the meeting, let me very briefly explain the background of this. The environment in education in Japan has been rapidly changing due to the declining birth rates within Japan and the effect of the so-called globalization from outside. The Japanese government is trying to the Japanese government has trying to prepare Japanese universities for the change in the higher education for the next generation as a serious challenge. This is how the top global university project with the Japanese acronym SGU was started by the Japanese government. So in response, Kyoto University, through its Japan Gateway project, will lead the movement to promote international cooperation with leading foreign universities, not only to produce the top-level research achievements, but also to foster the leaders of the next generation, ultimately aiming at the new system of academic degrees. So today, it is a great pleasure to hold the SGU Mathematics Kickoff meeting to celebrate the first year of the Japan Gateway project of Kyoto University. So I'm so grateful to the eminent speakers, Professor Erwin Boltzhausen from Universität Zurich, Professor Min-Hyung Kim from University of Oxford, Professor Herbert Koch from Universität Bonn, Professor Manfred Lehn from Johannes Gutenberg-Universität Mainz, Professor Bldg from Texas A&M University, and Professor Thomas Schick from Georg August Universität Göttingen, who have kindly agreed to participate and give talks. So we are all so anxious to listen to their talks. But since I have to leave before the end of the meeting, let me thank the organizers, especially the chair, Professor Takashi Kumagai, for the wonderful organization, and the supporting staff from Mathematics Department, and RIMS, whose collaboration was indispensable for the meeting as well as the whole project. Thank you.
Thank you very much, Professor Mori. So the first talk will start at 2:40. So please relax until please write down your name. There is a participants list in the back. Please write down your name.
On the 2 days ago, I came from Korea, so I was in the same time.
いや、なんかちょっと紹介してみた。ああ、そうですか。っていうことです。そうです。山口さん。僕もなんか王様の話。
I think I mentioned maybe over Very good. I had this effect. Maybe masters. It's a model, of course, we have not time to know it. So that's the next step. Investigate geometry. Examples. So far, geometric relevant structures and deformations, so you get very focused. But now he has, I think he can do it also. He should try to
So before we start, I have one announcement. During the break, we have tea, coffee, and some snack at room 108, which is just across this garden. Unfortunately, it's raining, but please go to 108. Okay, so we ask Professor Namikawa to chair the first session.
So before the talk, I will briefly introduce Professor Manfred Lehn. He was born in Germany in 1963, so he is a little bit older than I. Only a half month, only a half year older than I. And he is a full professor at Mainz from 2002. And Professor Manfred Lehn is an algebraic geometer. He is famous for the work on cohomology ring of Hilbert schemes. And his book with Heubrecht is also very famous. His book is now a standard text for the moduli space vector bundles. He will spend 4 months from this April as a SGU professor, and he's now learning Japanese. But his talk today will be in English. So let's start. His title is Rational Curves and Symplectic Manifolds. So please sit down.
Thank you. I'm looking very much forward to being here, and this will be very inspiring to be up to work here. And I must say I'm very grateful and thankful for this invitation. I mean, there are many Japanese mathematicians whose work have influenced me deeply and profoundly. And without their work, I mean, I could have done nothing. I mean, and many of them are working here in Kyoto. I mean, there's no need to point out Professor Fuchiki, Professor Mukai, but also Nakajima and Namikawa's work has influenced me profoundly. And I feel very honored to be here in Kyoto, to be around to work here. Today, I would like to speak about symplectic geometry, and I'm aware that not everybody in the room is an algebraic geometer, so allow me to introduce the subject gently. And so what is this all about? So the first thing I need to introduce is the notion of a holomorphic symplectic manifold. So by definition, this means that X. So X is a holomorphic. Sorry, X is a complex manifold, and omega a global holomorphic two-form. And to make it symplectic, we require that it's non-degenerate. So if we evaluate it on tangent vectors, this is supposed to give us an isomorphism into one forms. And moreover, we require it to be closed. So this is a notion that most of you will be well familiar with from classical analytic mechanics. And so what examples do we have? Well, the first example indeed is from mechanics. So these are called phase spaces.
So we're talking now about, so I can speak also audio, okay. So these are phase spaces. So this means I take any complex manifold, and then we can pass to its cotangent bundle. And of course, this cotangent bundle then has a tautological one form. Tautological one form, say lambda, and sometimes called the Liouville form. And then if we take omega to be the derivative, then obviously this is closed, and by a local calculation, it's easy to see that this is symplectic. And this example is non-compact, and the first compact example can be obtained just by taking on Cn. We have the standard form omega given by dq1 dp1 plus dqn slash dpn, and then this form will be obviously invariant under any translation because it's just constant. So if we choose a lattice in C2n, then we can form the quotient, and this form descends. Yeah, so this will be this gives a class of examples that complex tori, complex. In some sense, we don't really like both of these examples. For the applications that one has in mind, namely the classification of complex varieties with vanishing first Chern class, there's a certain structure theorem, the Bogomolov decomposition theorem, which allows to decompose such spaces into three types, namely tori, the so-called Calabi-Yau manifolds, and the hyperkähler ones, the ones that I'm really interested in. And for this, let me strengthen the definition. So we will say that such a variety is an irreducible holomorphic symplectic manifold if, in addition to the requirements that I imposed here, namely the existence of this form, I want X to be compact. So this excludes this example. I also want it to be simply connected. This excludes this example. And I want it to be of Kähler type, which means that it should admit a Kähler structure even though this will not play a role during the discussion. And this is supposed to exclude other examples, which somehow with an unwanted behavior. And the second condition is a condition on the form. I want the form to be unique. So this means the space of holomorphic two forms is generated by omega. I mean, all these conditions can be rephrased in a more differential geometric way by saying that the holonomy of this, so if you is the symplectic group for an appropriate chosen metric on that. Yeah, I should have said that, of course, because of this symplectic structure here, the dimension of that spaces always have to be even, so the real dimension is 4n. Okay, so what examples do we have in that case? And the first that comes to mind is the K3 surface, and to be specific, let me introduce the quartic K3 surface. So what we do is we choose a polynomial, say homogeneous in 4 variables of degree 4. And then we can take inside P3 the complex projective space. We can look for the solutions of this equation. And if we choose F generally or generically, then this will be a smooth surface, smooth, simply connected surface. And we do get a global holomorphic two form, which can be made very explicit in this case in the following way. If I take this 3 form, well, and now we alternate and if I divide by F, yeah, then you see that we have a 3 form on P3, which is well defined because of the correct homogeneity of this. I mean, we have degree 4 and degree 4 both in denominator and numerator, and this has a simple pole along X. So if we take the residue along X of this alpha, this will be holomorphic 2 form, and that's a very explicit description of this K3 surface, of the holomorphic structure of that surface. And then well, higher dimensional objects of this form have for some time been thought to be non-existent, and the non-existence had actually been proved. Of course, obviously there's a mistake, otherwise I would not speak on the subject. And in German we have this saying that a person said to be dead lives longer. Yeah, so here the fact that somebody tried to disprove these now makes it very difficult actually to classify these beasts. Yeah, they are putting all strengths to defend themselves against classification. And the first example that was found is due to Fujiki. And Fujiki observed that if you take 2 copies of a K3 surface and you model out the symmetry action, that then these things, clearly, you can pull back the symplectic form from here and the symplectic form from here, then we get a symplectic form which is symmetric. So if we mod out the symmetry, this will descend. The problem is this is singular, but Fujiki observed that if you desingularize this, then the symplectic form extends over this desingularization. And this example had then been generalized by Beauville, introducing the so-called Hilbert schemes. So the Hilbert schemes can be thought of as moduli spaces of points on S, but which are allowed to come together. And in case they come together, we remember additional information on the way these on the type. How these n tuples collide. So another way of thinking of this is by taking n copies of S, modding out the symmetry action. Of course, the singularities here are a bit worse than the ones in this example, but in some sense, it suffices to control what happens here in order to see what happens here, and then this will be a desingularization of the situation. Yeah? And an even further step was then taken by Mukai, and Mukai showed that much more. In more general, we can think of so-called moduli spaces of, let me put algebraic vector bundles. In fact, it's not sufficient, because if we take algebraic vector bundles only, then the corresponding moduli spaces will not be compact. So in order to compactify them, we have to allow degenerate versions of these vector bundles, which means we have to allow coherent sheaves. And as I will come back later on this construction a little bit, let me give a bit more detail here to this. So we fix again K3 surface S, and then if we have an algebraic vector bundle on S or a coherent sheaf, then we can collect the topological information about this vector bundle, meaning its rank and its Chern classes, in one inhomogeneous element, the so-called Mukai vector, so which by definition is the Chern character of E times some element that comes from only from the surface, so the square root, the formal square root of the tot genus. So this will be an element in the integral cohomology of the K3 surface. Yeah, this is the Mukai vector, and this encodes, as I said, encodes rank and Chern classes. And now the point is that if we take the set of all such vector bundles that have a fixed Mukai vector, and we put on some stability conditions, allow me to ignore this issue of the stability now, because it's a bit technical and it's not really important for the storyline. Then this turns out to be a projective irreducible holomorphic symplectic manifold. So I will not speak about this stability condition, but what I would like to speak about is where the symplectic structure comes from in this case. So if we take a point in this moduli space, then by definition it has a modular interpretation. So the point has an interpretation as a bundle or sheaf on the underlying surface S. And this moduli interpretation can be used to describe the tension space. I mean, of course, here it is completely useless to talk about equations or anything like that. So it's really important to have a different interpretation of that space. But the tangent space of this
can be interpreted in a canonical way
as
the extensions,
as the self-extensions of this sheaf with itself. So a tangent vector corresponds to a sequence E this type. So this is very important in the sense that we can use the intrinsic geometry of the sheaf that represents the point. So this is geometry on S. This can be used to give an interpretation of the tangent space to M. So in particular, if we want to talk about symplectic forms, it means that what we really need to do is we need to describe a skew-symmetric pairing on X. Well, if I write it down like this, then anyone in the audience will probably just by reflex say, well, there's a cup-product mapping this into X2. Yeah, so we will go into X2, and then here we have the trace map sending this to OX. And this is the point where it becomes important that we are on a K3 surface and not just on any other surface, because now we can evaluate this by integrating against omega, which is, I mean, so this is can be read as an anti-holomorphic 2 form, so a form of type 0,2, and this is a form of type 0,2. So by smashing it and integrating, we get a map, and this map is a non-determinate pairing, and this is the omega S on the surface, but the total map can be read as the omega on the moduli space. Yeah, so we have a very natural interpretation, and to verify that this all works out, that things are smooth, and is this major result here. And then, well, there has been work by Heubrechts, O'Grady, and finally, I mean, Yoshioka, who showed that unfortunately all these moduli spaces that we have produced here are again deformation equivalent to the Hilbert scheme. And this is up to two exceptional examples of O'Grady. This is still the case. We have I mean, even since in the last 20 years, there have been not found any new topological types. Still, there can be new varieties, even if they are of the same topological type.
What does it mean, deformation equivalent?
If you have a family of such varieties, so the underlying differential C-infinity manifolds are all isomorphic, but the complex structure varies. So, and it is possible to show that these manifolds are actually not isomorphic. They're really different from the Hilbert schemes, but it's possible to produce one or perhaps even several families, and so that in the end you end up with the Hilbert schemes. So in that sense, they are deformation equivalent. Okay. So I said that all examples that we know are in some sense related to these moduli of sheaves on K3 surfaces, but there has been for a long time one other family which somehow for a long time looked a bit obscure. And this was the family that was produced by Bouville and Donaghy. And so and this brings me back to the main subject of my talk. And so let me introduce. So here the main hero is the K3 surface, and everything takes place on the K3 surface. And I want to replace that now by a different actor, which is the cubic fourfold. So enter cubic fourfolds. So let me fix now. As before, but now this is a homogeneous polynomial of degree 3, yeah? And we have 6 variables. So we get in P5, we get, let me call this Y in order to distinguish from anything what I had before. So again, this is the set of all solutions of this equation. And if we take f, again, very general, this will be smooth. And there is some technical assumption that will be necessary, not in all places, but almost everywhere. So let it make from the beginning, that there should be no plane. Yeah, no plane should be contained in Y. This can be by generic choice of f. This will be the case, so there will never be a two-dimensional complex space contained in Y. So allow me to assume this for the moment. So this is a surface of degree of degree 3, and we call it a cubic fourfold because it's four-dimensional. And then the interesting thing about this is that the Hodge diamond. So this is the collection of Hodge numbers of this variety. Takes the following shape. Yeah. And I want to draw your attention to this piece. I mean, it has, of course, this funny symmetry because of Poincare duality and Serre duality, which enforces this type of picture here. But for us, particularly interesting is this one element here, and how to get that. So let me imitate the construction that I wrote down for the K3 surface. So in the denominator, I have something like -1 to the I xi dx0. Then I leave out this one, dx5. But now you see that in order to get something well defined, I have to balance this degree 6 thing on top, and so I'm forced to take f squared in the denominator. Again, this will be a well-defined meromorphic form on the projective 5 space, which has now a double pole on Y. So I cannot simply take the residue of this to get a holomorphic thing, but by Griffith described the procedure that it's still possible to get a form which is well defined on Y, but this form is no longer. Allow me to call it alpha. This will be it will be a form of type 3-1 on Y. Yeah, so it will be has three holomorphic and one anti-holomorphic. The construction is basically the same as in the residue case. I mean, if you think of Y, and so I need to define how this form integrates against any submanifold. Well, extend this submanifold to something four-dimensional in a small neighborhood, and then you integrate this form against it, and then this will give you. I mean, this will define this form alpha. Yeah, but because it's a double pole, it will not be holomorphic. Okay, so and this is a unique section, and it is responsible for this one that occurs here. So what can we do with this? Sorry. So what can we do with this? So assume that we have the following situation. Assume that this is a family of curves, of smooth curves on Y, parametrized by a base B. Yeah, so this is a family of smooth curves on Y, parametrized by let's say a smooth base, by a smooth base B. So here we have a total space, and for each point in the base, each closed point here, there will be a certain fiber over it, and this fiber will be, via this map, be embedded into Y, and if the point B varies, we get a varying family of curves on Y. So what can we do in that case? I have the pullback map from Y, and I have the projection to B. If I take this form alpha, I can pull it back to C, and then I can integrate along the fibers. By integration along the fibers, of course, I will reduce the type. Instead of having the type 3, 1 via integration, one holomorphic, one anti-holomorphic direction will vanish, and the resulting form will be a 2, 0 form on Y, on B. Yeah, so we get, let me write it like this, we will get a form on B, which is obtained, well, pulling back alpha and then integrating, allow me to write it like that, we integrate along the fibers of B, and this will be a holomorphic 2 form on any base B. So the lecture we take from this simple construction is that whenever we have a family of curves on Y, we will obtain a holomorphic 2 form on the base B.
Q star alpha should be P star.
Ah, sorry, yes. No, this picture is wrong. It's right. Okay. So this is the generic phenomenon, and now let's start to see it in detail how we can use this to produce symplectic manifolds. And historically, the first case was obtained by Bouville and Donaghy. They looked at the following. I mean, they investigated the so-called Fano variety. Of Y. So by definition, you can think of this as being all the lines. So L is a projective line, isomorphic, abstractly isomorphic to P1C, and of being of degree 1, and this sits inside Y. Yeah. Of course, if it sits in Y, you can also think of this as sitting inside the P5. So this will get a topology as a subspace of the Grassmannian of two-dimensional subspaces in C6. Yeah, so this is the Fano variety of lines. It turns out that this thing is smooth of dimension 4. And via this procedure, it carries a symplectic structure which is non-degenerate. So, omega Fy. I mean, this of course is a special case of that construction. Is non-degenerate. It's non-degenerate. In fact, Bouville and Donaghy showed more, namely if Y is of so-called Pfaffian type. Let me just mention this for the moment, and I might come, if I find time, on this question later on. So if Y is of Pfaffian type, then this space turns out to be isomorphic. So here, of course, this is the disappointing part because we are back to the old examples. Turns out to be isomorphic to the Hilbert scheme, second Hilbert scheme of a K3 surface, as a K3 surface. Okay. But still, I mean, as I said, I mean, this example is rather old, and is a bit surprising because I mean, there's no K3 surface. Apparently, there's no K3 surface showing up in the construction. Yeah, and then for some time, not much happened in this direction, and then De Jong and Starr looked at it a bit closer. And they try to generalize this in the following way. They said, well, let's define. Well, this is my notation nowadays, but basically all the results that are here are due to De Jong and Starr. So let's define this as being the closure in the Hilbert scheme of Y of the open set. Of the following set, namely MDY0. These are rational curves on y. So C is a rational curve, smooth. So it's abstractly isomorphic to the projective, one-dimensional projective space, but it's embedded in such a way that it has degree d. It's degree d. Yeah, so it has a kind of twisted embedding into this. So if you choose d equals 1, you get this example. Yeah, so this is a higher dimensional case, a higher degree case. And then, of course, by the same procedure that I explained over there, we will get the holomorphic 2 form.
Omega d, holomorphic 2 form.
At least on the open path. Okay? And then de Jong and Starr showed two things. The first was that, among others, that this form actually extends as a holomorphic form on any desingularization of that space. So this might be singular. No one knows in general. This might be very singular. But they showed that if you choose any smooth compactification of that space, then this holomorphic 2 form will extend as a holomorphic 2 form. The point is it's in general not symplectic. And so what happens is the following. If it's not symplectic, then we can measure its failure to be symplectic by looking at the dimension of its kernel. Or in the case of a symplectic form, we perhaps better should speak of its radical. Yeah, so we look at the dimension of the radical, and then they found the following table, namely if degree is 1, 2, 3, 4, 5, 6, 7, say 8, then we can look at the dimension of the kernel of omega d at a generic point. So that's a generic calculation. Then they found the following numbers. And from now on it becomes 2 periodic. So how should we interpret these numbers? Well, I should perhaps also give you the dimension of that space. Yeah, it's a bit strange table now, but so here we have 4, 7, 10. I assume you can guess the rules. Yeah, it's 22, 25, and so these are the dimensions of that space. So how should we read this? If you, for example, take d equals 2, then the moduli space will be 7-dimensional, but the form has a rather large kernel of rank 3. Of course, it certainly cannot be symplectic anyway because the dimension is odd. Yeah, but we can measure precisely, or they can measure precisely the failure for this generically. And let me explain what is the geometric reason for this failure. That's because it's easy to see. Well, let's do the following. So we assume d equals 2, and I take in that space of curves of degree 2, I take a point. So this point corresponds to a curve of degree 2. The curve of degree 2 is always a plane conic. So C in Y is a plane conic. So in particular, if I take the linear hull, so this is the smallest linear subspace in the projective space that contains C, then this will be a plane. But this means conversely that if I take Y and I intersect it with this plane, you remember that I imposed the condition that my Y should not contain any plane. So this means this plane is not contained in Y, or in other words, Y, the intersection is a proper intersection. So this is a hypersurface of degree 3. It intersects C therefore in a curve of degree 3. This curve of degree 3 contains C. So the curve obviously must break up into something of degree 2. Well, what is left is something of degree 1. Something of degree 1 is necessarily a line. So we have the curve C and a residual line L. In this way, we get a well-defined map from M2 of Y back into M1 of Y, sending a point that corresponds to this conic to the point corresponding to the residual line of that. conversely, so I mean, picture of this is, well, I'm not sure. I find pictures helpful, but so this is very symbolic. Yeah. So this is y of degree 3, and if I take the plane generated by C, then this plane will intersect the conic in one more line. Now, conversely, if you fix the line, how can I get a conic? Well, you simply take all planes that contain that line and just reverse the construction. So if I have a plane, this contains the line, I intersect it with y, then there will be a residual curve, which is a conic. So this means that actually this thing, the fibers are just given by all planes that contain the given line, and this turns out to be a P3. So here you see perfectly why this form fails, because one can verify that the form on here is a pullback of the form on there, and it clearly is trivial along the fibers of that fibration. So the kernel of this will be three-dimensional. So if you see this, then the next interesting case will be the case of cubics. And so this paper is from 2004, and so we we looked at this degree 3 case, and indeed in that case we found something interesting. So let me speak on degree 1. So degree 3, and here I want to give you two theorems, and then I want to explain part of this, and then I will finish with some speculations. So here this is joint work with a former student of mine who by coincidence has the same name, and so Christian Lehn and then, of course, my standard collaborator, Christoph Sorger, and my colleague Duco van Straten from Mainz. So the first observation we made is that, and that was a big surprise for us, and this is not automatic. It requires many calculations. This is not, I mean, sometimes smoothness you get for free, but this smoothness is hard work. Yeah? So it turns out that this thing is smooth, yeah, it's smooth projective. Of dimension 10. And the second thing is, so you see that we should contract 2 dimensions. If there's any chance to make it symplectic, we should contract 2 dimensions. It turns out that there exists an 8-dimensional irreducible holomorphic symplectic manifold Z, which depends on Y, and there are also morphisms. So from the space of cubics down to Z of Y, and also an embedding of Y itself, which is quite surprising. And of course, this embedding has to be a Lagrangian embedding, but this is automatic given the topology of Y. Once you find an embedding, it automatically has to be Lagrangian. And it turns out that this morphism actually has a very, very nice structure. Namely, if we take the blow-up of this variety along that subspace, so here we take the blow-up of Y along that space, then it turns out that this factors over this, and this is a P2 bundle. Now, P2 as a fiber bundle with complex projective spaces as fibers. And well, to complement this is we have the following theorem. This is in collaboration with Nick Addington, and here we show that first of all this space. So if Y is of Pfaffian type, then Z of Y is birational to a Hilbert scheme hilp 4 of S. And there's another statement here, which I will perhaps postpone until I have a chance to introduce the notations for that. So this again means that, I mean, any of these they are not, so by a theorem of Heubrecht's, if something is birational to a Hilbert scheme, then it's actually deformation equivalent to a Hilbert scheme. And if, well, anything else is certainly deformation equivalent to these ones. So our new family will be, again, deformation equivalent to Hilbert schemes. However, the family is new in the sense that it's a complete family. So we have, this is the first family of 8-dimensional irreducible holomorphic symplectic manifolds, which really sweep out the maximal possible deformation dimensions for holomorphic projective manifolds of this dimension. So there, of course, there are 8-dimensional Hilbert schemes, but they form a divisor in that. And so that's the, in dimension 4, we have now several constructions by many people, Iliev, Ranestad, Manivel, O'Grady, and so on. So we have many constructions of 4-dimensional complete families, but this is the first 8-dimensional complete family.
So you said that there's a lot not known about these IHSMs, but you know the dimensions or structure of their deformation spaces.
I mean, of course, we know lots of things about the deformation space. Yeah? I mean, the deformation space. I mean, these things are well studied. I mean, in some sense, we know that there are stuff out there, but it's not easy to get precise constructions for them. Yeah? So it's so now I have 20 minutes left. So, I mean, I could speak about the geometry of this, but I could also speak about this fourth point, namely to relate that to the symplectic structure and the derived category. Perhaps I do the second thing and will leave out the geometry and will speak about the derived categories. Is that okay, or should I speak about the geometry? What do you prefer? Now it's a choice. We can take a vote. Let me speak a little bit about the geometry first. And
I ask another question.
Yep.
You have this function type condition. Is it a restrictive condition or is it?
Which condition?
This function type, which now showed up twice.
Okay, so let me explain that first. Yeah, so Pfaffian type is a divisor in the moduli space, and so the idea is this. So let U be an abstract 6-dimensional vector space, and then we can take lambda 2 of. We take the projectivization of this, and we take the projectivization of its dual. And then inside here, this has so this means these are 6x6 skew-symmetric matrices. Then we can stratify that space by the rank of that matrix. If the rank is a generic degenerate, it means it's a hypersurface. This is a hypersurface of degree 3. So these are the Pfaffian, the skew-symmetric matrices of rank 4. And then inside here we have rank 2 matrices, but this means exactly the Grassmannian. So here we have the Grassmannian of this is 2-dimensional quotients of U, and on the other hand, here we have exactly the same thing, just everything dual. Yeah, so here we can think of this as being 2-dimensional subspaces of U, or as 2-dimensional quotient spaces of U star. And then let's say we take here a generic 5-dimensional subspace being given by a 6-dimensional subspace of lambda 2U. Then if I pass to the orthogonal complement, I get something which is, this is 15-dimensional. This will be 9-dimensional, and then here we get some 9-dimensional vector space. Okay, so if I intersect these two, then I get a cubic hypersurface, and this is a hypersurface of Pfaffian type. In other words, a hypersurface of Pfaffian type, if its equation can be written as the Pfaffian a 6 by 6 skew-symmetric matrix. If this is possible, then it's of Pfaffian type. But you see also here that due to this construction, there will be this intersection. This is a P8, of course, not a P9, because we have a 9-dimensional space. So projectivizing it will become P8. This one is 8-dimensional. This is 14-dimensional. So you get a 2-dimensional, and this is a K3 surface. And this is the K3 surface that shows up in both ways. And now you have, I mean, you can imagine that there's something, I mean, holomorphic projective dualities that relate the two things, and you can do lots of geometry to change these things. And
without the condition, you get some exotic.
Pardon?
Is there hope that without the Pfaffian type condition, you get something exotic?
Well, it depends on what you mean. It's exotic. It's definitely not Hilbert schemes. Okay. Yeah, but still deformation. So the topology is the same as the one of underlying Hilbert schemes. So let me try to explain how this wire shows up in the construction. Where does it come from? The point is this: if we have a line, then it's a line. Nothing can happen to it if it degenerated. If you have a conic, you see immediately that this can degenerate in many ways, and in order to get something compact, you actually need to consider these things. If we now look at whatever signs I draw, it's very difficult to read, right? So let's now talk about the degree 3 case. In the degree 3 case, the general object will be a so-called twisted cubic. And if it's smooth, it really looks like this if you draw a real picture for it. Yeah? But it can degenerate, but it can degenerate now in many, many different ways. And there's one way, say, for example, it can break up into different components and so on and so on. But it can also degenerate in the following way, namely that somehow you flatten the curve until it is completely contained in the plane. Then you will get a singularity here. Now, if you check the cohomological, the Hilbert polynomial of this object, then the Hilbert polynomial of this one is 3n plus 1, and the whole Hilbert polynomial of this one is only 3n. And in order to get the Hilbert polynomial correct, you have to add one more point, and if you do it in a flat way, I mean, if this is, I mean, let's say smooth, yeah, or continuous deformation, yeah, to this one, then it requires a so-called embedded point. So the curve will be plane, but in some sense, the reduced curve will be plane, but there will be a non-reduced point. And the non-reduced structure is chosen in such a way that it sticks out. And there's a unique way of doing it inside a given P3. And so we get these two types of curves. This one is the generic behavior, and these curves are called arithmetic Cohen-Macaulay. Because if you take the cone, I mean, these are curves in P5. If you take the cone over them in C6, the affine cone over it, then this will produce singularities which at the origin are still arithmetic Cohen-Macaulay. So they're sort of mild. And whereas these ones are really, really singular, they are not even Cohen-Macaulay, yeah? Let alone arithmetic Cohen-Macaulay. And now, so the picture now is this. We have here the manifold, I mean the space of this 10-dimensional space of cubic curves. So if I take any cubic curve here, the linear hull of this one, this is quite surprising, is not at all evident. The linear hull of this one will be a plane, a 3-plane. So we get a well-defined map to the Grassmannian of 3-dimensional subspaces in P5 by sending the curve to its linear hull. And then this map factors, we can take the Stein factorization, which is, so this is a finite map. It turns out that it is finite 72 to 1. And the generic fiber is related to the root system of the exceptional group E6. That's why there are 72. And then we can take the desingularization of that space. and this factors and is a P2 bundle. And then inside here, I said this one is the generic behavior. This is the unexpected behavior. So here we have a divisor sitting of the non-Korn-Macaulay curves, and under this P2 vibration, this becomes a divisor in Z prime, and then we have this final contraction down to Z. So what happens on that step? The point is that on the way down to Z, it turns out that all information about the curve gets lost, except for the information about that point. What is the reason for this? There are many ways how to look at that. In particular, why this is just y? How do we get such a curve? Well, there's the following way: we choose y, and then we need to produce that curve. And the only way to do this is to choose a P3 down here, so this linear curve, in such a way that it does not intersect transversely at the tension space. So it should be contained in the tension space in the projective tension space at this point. And afterwards we choose a plane. But by this map we get rid of the P2 bundle. What is the P2 bundle? Well, the P2 bundle simply is the choice of all possible P2s that go through this point and lie in between Y and P3. So having got rid of that P2 bundle, we have only this left, and then the final contraction just forgets about this choice. And what is left is the point Y. So all these different fibers, all these different curves that go through the same point, they are all mapped down to Y. There's a much better interpretation for this if we pass to the derived category. And now I have 7 minutes less, so let me explain about that. So let me come back first to Mokai's example construction. What is the reason there? If we take say now we are back on S, on a K3 surface. Suppose I have two coherent sheaves. I take two different ones, and otherwise you will not see which one is E and which one is E. If I call them E and F, you will see which is which. So I have the homomorphism from E to F. Then by Serre duality, I can write this, or let me write this more generally as xi. Then by Serre duality, this is 2 minus I Fe, and then there's a twist coming in, because I need to twist with the coherent. So this is Serre duality in general for an arbitrary surface. Now, if we're on a K3 surface, then of course omega s is trivial, so I can get rid of this. If I rewrite this now in terms, instead of working with coherent sheaves, I go to the derived category of coherent sheaves on the surface. So in some sense now E and F are allowed to be complexes. Also I write, instead of X, I write hom, but I allow F to be shifted in the category. Then this whole thing can be written as om, and this 2 here becomes just a shift. So the point why all this works is that on S, the derived category has this fundamental property that the Serre functor here is just shift. It's shift by 2. So this is the crucial property that makes things work. Yeah? And so let's see what happens. What is the situation about Y? Certainly Y has the canonical bundle is, the anti-canonical bundle is positive, so the canonical bundle is very negative. So we do not have such a situation. But Kuznetsov analyzed this in the following way. He said that the derived category of Y has a decomposition, a so-called semi-orthogonal decomposition. In the following way. So these are the standard line.
This is the standard line.
Positive standard
Line bundle on Y.
comes from its embedding, and this is the trivial bundle, and this is the negative twist. By definition, that category consists of all objects in the derived category such that there are no morphisms from the right to the left. So in that sense, this is it's the right orthogonal complement in the categorical sense of this. Yeah? And now the key observation is that this thing behaves as if it were a derived category on a K3 surface, almost. Yeah? So this thing, AY is a Calabi-Yau 2 category. Calabi-Yau 2 category, or two-dimensional, it's better to say, category. So this means that we have exactly this behavior. So I mean, of course, one has to distinguish between the self-functor on the full category and the self-functor on that subcategory. So this subcategory has its own self-functor with the shift by 2. And this means that objects in that category behave as if they were sheaves on a K3 surface. And this has the immediate consequence that x1 is dual to x1, that x2 is dual to Hom, which is not the usual Serre duality on Y, and this will be non-degenerate. So what happens? Oh, now I erased the wrong blackboard. Of course the question is how to get in there. So given starting with any projective, say coherent sheaf, in order to get there we have to start on the right hand side and do projections in the derived category, as so-called left mutations, which takes an object and bring them into this category. And this in some sense, if I now look again at my picture of this situation, and here this P2 bundle, and here we have this final contractions, then it's actually you can verify that this corresponds exactly to the projections, to the left mutations that take place in this situation. So, for example, if you start with a curve which is arithmetically called Macaulay, then already this left mutation stuff stops one step earlier than in the other case, and in each case, I mean, as usual, when you do a projection in linear space, you lose information. Yeah, if you just project something, you lose all the information that happens in the fiber. And the same happens here. And this process of forgetting information is the one that takes the curve here. So this one really parameterizes curves, but this in the end is no longer parameterization of curves, but of equivalence classes. And that process forgets exactly the same piece of information that you forget there. So in the end, we come back to the fact that the true reason for the appearance of the complex, of the symplectic structure lies in the existence of this Kuznetsov category here. And well, that's what I wanted to explain. So unfortunately, I'm being recorded. Yeah, otherwise I would go into some speculations. Yeah, but that's a bit too dangerous to be recorded. And because I could speculate, for example, what happens if the degree is not 3 but 4 and 5, but perhaps we can switch off the machine and you can ask questions. And then there are some more speculations about the connection with matrix factorizations, and which is in fact the tool that my colleagues and I used while we were preparing this geometric work. We were doing computations on the computer using matrix factorizations, which helped our model, because for a long time it was not. I mean, finally the picture is very simple, but at the beginning, I mean, this was not so obvious what was going on. But doing calculations with matrix factorization, we knew from the very beginning that the tension space was 8-dimensional and symplectic in every point, even in the most degenerate point. For the matrix factorization, it was 8-dimensional symplectic. So this was some of the moral background that we needed to carry out the work. In the end, in the paper, the word matrix factorization does not show up, but somehow I think that it might be, at least for these hypersurfaces, might be the right context to do it appropriately. And once you have reached this level, then actually we could drop the notion of a curve completely, because if you take this point of view, there's no reason to talk about curves. Yeah, I mean, this is something about the derived category of coherent sheaves. So you could fix any type of topological data, say in any element in K-theory, and carry out that construction. The problem is why we work with curves is that with curves we have some control about the geometry. If you just take a sheaf on a cubic fourfold, what do you want to say? I mean, it's almost impossible to get your hands on the geometry and to do anything. And so that's the only reason why we work with curves. Otherwise, we could take coherent sheaves as well. But this is for the moment out of view. And my hope that it will be, we will get a more direct approach to it by investigating matrix factorizations in more detail and make that connection precise. And this is one of the projects that I have in mind when I can quietly work here without being disturbed by too many students at home. Thank you.
Thank you very much. Are there any questions or comments?
Thomas?
I have once again, yeah. So I don't understand the connection between the curve picture, which is
Yes.
kind of abandoned, and the derived category picture. I mean, you're saying there's abstractly some equivalence.
Yeah, I mean here, for example, here you do the following. Just to give you this map here, you start with the ideal sheaf of the curve in Y. This is more or less the same thing as giving the curve. Yeah, because there's a unique, I mean, even the abstract, I mean, with an ideal sheaf, you always have to be careful when people say ideal sheaf, they always think of the sheaf as being a subsheaf. Yeah. So, but here there's no difference. If you have this ideal sheaf or the ideal sheaf as an abstract sheaf or as a subsheaf, it's the same thing. However, if you now say, I said that the curve S generates a three-dimensional. So this is a P3. If I intersect this P3 with Y, I get a cubic surface. So this is not, that's a different S, so sorry, let's say sigma. Yeah? So I get a cubic surface. And so I can consider this also as a subset, as an ideal sheaf of C as being considered in the cubic surface. And I can consider this still as being a coherent sheaf on Y. Now, the interesting thing is that, of course, starting from this, I easily get down here, but there's no way back. And the reason is that this curve has many embeddings into the structure sheaf. This thing has codimension 3, but this thing has codimension 1. So there's a linear system in general of possible embeddings. So here there's a difference between the notion of the sheaf and of course, for a smooth surface, this will be a line bundle, yeah, and this linear system in the real sense of the word. Yeah? But even if this is very singular, both of them can be very singular, then there will always be a P2 of possible embedding. And again, I mean, so for example, if you have if you take a curve which looks like this, with this embedded point here, then we get the following. I hope I get this right now. So I have the curve, I have the embedded point, and here I get the reduced curve. Yeah? But now keep in mind the reduced curve is a complete intersection. And the complete intersection is of such a type that when you apply the projection here, then this will completely disappear. Because this has a resolution which involves only these three line bundles. So if I do a projection which gets rid of these three line bundles, it means that, I mean, first of all, line bundles that take twists. I'm very imprecise here, but the basic point is that this sheaf under the projection gets ignored. It becomes zero. This means that if you project down into this category, then the curve and the point have the same information. And that is the reason why for this divisor, all the information gets lost except for the information on the embedded point. Yeah, so here geometrically you do
This construction actually,
which we do using arguments from Mori theory. I mean, we have contraction arguments and checking intersection numbers and so on. So like in the Middleman model program, I mean, we just verify that the construction exists. In this interpretation, this has a very precise meaning, namely, it identifies C with P because the difference between them is information that is projected out by the left mutations in the derived category.
So you claim that AY is nothing but the derived category of Z? AY, the subcategory AY, is isomorphic to the derived category.
I mean, these are semi-stable objects in AY. So this is a kind of modularized space of semi-stable objects in AY for some semi-stability, for some stability condition on the derived category on AY. The problem is that so far we have no theory for that. So we are lacking projective, we are lacking constructions to associate abstractly to a stability condition and projective moduli space.
And how do you prove that Z is deformation equivalent to Hill?
Well, this is Eddington calls it the quick and dirty proof. Yeah, so it's a bit of cheating proof. Yeah, so what we do is the following. Think of Y. We are in the Pfaffian situation, Pfaffian case now. We have Y and we have S. Then over this, there's a certain incidence scheme. Let me call it gamma, which is 4 to 1. So I think let me see whether I can still reconstruct it. So this here we can write this as being forms. So let me think. So a point here is a two-dimensional subspace in U, and here I have a form on Y whose radical is two-dimensional because it has rank 4. So it has a kernel, and the kernel is two-dimensional. So each of these two represents a plane in some sense. And then I can impose the condition that this intersect, that these two planes have a non-trivial intersection. This is the definition of this gamma. So the gamma is the space of all pairs such that the corresponding two planes intersect. Yeah? And this gives us a kind of incidence variety in this, and this will be the Mukai kernel for a certain Fourier-Mukai pair transformation from gamma to S. And this one is 4 to 1. So, and as I told you, I mean, because of this procedure here, I mean, a curve of this type is more or less the same thing as a point. So let me ignore details for the moment. Yes. So this means that if I do now the Fourier-Mukai transformation here, using the ideal sheaf of gamma as a kernel, I can let me do it very naively. So what basically happens is I have a point here, then the pre-image is 4 points. I push them forward, there are 4 points. Yeah? So what happens in the neighboring fibers? So the point is, in the neighboring fibers, there are other sheaves, there are other complexes. But now we have a kind of semi-stability argument. If you have complexes, and for some point under this transformation, the image is a sheaf, then in an open neighborhood it will also be a sheaf. And if the image sheaf is an ideal sheaf, then in an open neighborhood, the image complex will also be an ideal sheaf. So in some sense, if we have our moduli space set, and here we have the Lagrangian subvariety Y, then in a neighborhood of this, the image will be in the Hilbert scheme. So that's what I mean by quick, yeah, and because we do not analyze what happens outside Y, we only analyze what happens on Y, and on Y we get a well-defined map into the Hilbert scheme, using semi-stability arguments for cohomology, I mean for this transform, then we conclude that it also on an open neighborhood maps into the Hilbert scheme, and then we are done. Yeah, then we have a birational map by comparing the dimensions of the tension spaces. They have the same dimension and everything, and it's fine. So it's a bit. Yeah, we are lazy. We do not analyze anything what is going on outside Y. And I think Kuznetsov has started at the same time a more detailed research, and perhaps he will be. Actually, it's not excluded. Could be that it's actually isomorphic. Yeah, but our method does not show it. Our method only shows it's birational, because we have no control about what's going on here. And I believe that Kuznetsov can perhaps show that it's something much stronger is true.
Any other questions or comments? Then let's stop. Let's